Hi, and welcome to Fraction Division Part 1. I'd like to start off this video by demonstrating how I learned how to divide fractions many years ago when I was in school, and how I did it for many years before I figured out what it all meant. So I would have been given a question like this one: 4/5 divided by 2/3. I knew that I had to leave 4/5 the way it was. I knew that I had to change my division to multiplication, although I didn't know why I was doing this. And I also knew that I needed to use the reciprocal of uh, 2/3. Again, I didn't know why. And because I'd already learned how to multiply fractions, probably not understanding what I was doing, but I knew how to do it, I was able to come up with this answer and simplify it to 6/5, and then get it right. So I knew how to do it. I knew how to get the right answer, but I had no idea what it all meant. And I suspect that that is true for many students these days, so many years after I was a student in elementary school. Um, and part of the problem is this adage right here. And many of you have heard it: yours is not to reason why, just invert and multiply. And I think what a terrible thing to tell a student, that they should not ask questions why, just take this procedure and use it. Our job as math teachers is to make sure that students come away proficient in procedures, but also understanding the concepts that underlie them. When students understand these concepts, they make sense of these procedures and then use them properly as they are needed. So for this video series, I want to eventually get around to taking a look at the invert and multiply algorithm and investigating what is happening there, so that we can all understand it and pass this knowledge on to our students. But we have a few things to take care of first. John Van de Waal and his colleagues say that the division of fractions is one of the least understood topics in the K-8 curriculum, and the algorithm is described by them as mysterious. At least that's what the common perception of it is, and so we want to dispel this at all costs. So we're going to be taking a look at division today. Okay? Now sometimes we don't actually need an algorithm to divide by fractions, right? So let me give you an example. If I am going to the hardware store and I need to buy pieces of chain, I'm just going to change my app here, and I need to purchase 3/4 of a meter of chain from a spool of 1.5 meters. We can easily visualize this or use an app such as this one here to make a picture of what it looks like, to make a representation. So I am going to select quarters. Yes, I do want to change that. And the spool is 1.5 meters long, so it ends there. And I'm looking to get 3/4 meter lengths. How many can I get? Well, here is one chunk, that's 3/4 of a meter. Here's another chunk, that's 3/4 of a meter. So I can say that 1.5 divided by 3/4 equals 2. And I didn't need to use an algorithm. I didn't need a procedure, because I could visualize, or I can draw what it looks like, and sometimes that is the most expedient way to divide, and perhaps it's more reliable. So as with other operations, it's important to connect the division of fractions to its whole number counterpart. As I mentioned in my multiplication videos, students have a tendency to lose the meaning of the operation once fractions are involved. So we want to start with whole number operations and gradually move them into using fractions, and maintain that understanding of what the operation means along the way. So to that end, it is helpful for students to know, and teachers, that there are two interpretations of division. There's the measurement interpretation, and there is the partitive interpretation. Um, the measurement interpretation goes like this: you have a certain number of things, and you need to make groups. You know how much you want in each group, but you're not sure how many groups you're going to have. So if I have 12 cookies and I need to put them into groups of 3, how many groups of 3 can I make? And you can imagine somebody uh, gathering the cookies into piles of 3 and ending up with 4 piles. That is measurement. And this can also be achieved through repeated subtraction. So I have my 12 cookies, I take away 3. I take away 3 more, I take away 3 more, I take away the last 3. How many times did I subtract? That's how many groups I made, and it's 4. The partitive interpretation is the opposite. There's an amount, and you're going to be sharing that whole. We know how many groups to make, but we need to find out how many per group. So if I have 20 cookies this time, and I'm sharing them with 5 friends, I need to figure out how many each friend gets. And I could distribute them evenly, 1 to each, and then another to each, and so on, until I see that each of my 5 friends has 4 cookies, which I guess that means I have none, but that's neither here nor there. So working with these two interpretations and having students see the difference between them is a good idea, and gradually move them into the use with fractions. So I want my focus today to be on the measurement interpretation because that's where I see us making more sense of the invert and multiply algorithm. But I don't want to leave partitive alone. So let's take a look at an example of how that might look with fractions. And I'll head over to my RODS app to model this. Okay, so if I had a question like 6 2/3 divided by 4. So I have 6 2/3 chocolate bars, and I have 3 friends, including myself, that's 4, and we need to share them. How is that going to look? So what I'm going to do here is I'm going to put that marker down. I'm going to change this to fractions, and I'm going to set, or it already is set. The dark green is my whole. So I'm going to take out, oh, I've lost the question, didn't I? So let's just put that up as a reminder. 6 2/3 divided by 4. What's the answer? I'm sharing out these chocolate bars. So I'm going to create 6 2/3 right here. So I have my 6 and my 2/3. So these are the chocolate bars that I have, and I need to put them into 4 groups. I just don't know how many to put in each group. So I might share them out, kind of like this. 1 for you, 1 for you, 1 for you, 1 for you. Now that was easy, but I have a problem with the rest of it. So I'm going to take this whole chocolate bar and replace it with 2 halves and get rid of that. And I will do the same thing down here. So the amount is the same. And now I can take these halves and I can distribute them to the 4 groups. This 2/3 of a chocolate bar, I'm going to have to do the same thing. I need to break it into 4 equal groups so that they can be shared, and those groups are going to be sixths, because 2/6 equal 1/3, so 4/6 equals 2/3. Now I can just get rid of that before it gets in the way, and I can divide these up. So this is partitive division with some fractions. So the answer is, how much of a chocolate bar does everybody get? And if I grab this again and kind of compare it, yep, that is 2/3. So it's 1 2/3 chocolate bars, and that will be our answer. So each individual gets 1 2/3 of a chocolate bar. This is the sort of thing that kids need to see, students need to see before the algorithm comes up, because they really need to understand what is happening with that division. And this representation is a particularly strong one. So the procedure should be the last thing that they see. This investigation into what is actually happening in this question, that should be what they're doing uh, up front. First, working on whole number fractions, whole number division rather, and then moving into some division with fractions. But I said I wanted to focus on the measurement interpretation because I see more of a connection between it and the algorithm. So we're going to flip over to that. So let's clear this. So remember, in the measurement interpretation of division, the size of the group or groups is known, but we need to find how many groups there are. So let's consider, and you would be beginning with a whole number questions, much like the one I talked about before with the 20 cookies divided into groups of 4. How many groups will there be? Get kids thinking about what that means, and then bring in some fractions with a question maybe like this one. So let's consider that 1 serving of pizza is 1/2 of a small pizza. That's what qualifies as a serving. And there are 3 complete pizzas, and how many servings would that make? So that ends up being, I have 3 complete pizzas, and I know that a serving is 1/2 of pizza. How many servings would that be? Now, I like to live in a world where pizzas are long rectangles. So that's what I'm going to do. So there are my 3 pizzas, and 1/2 a pizza is a portion. So how many portions or servings can I get out of this? And if students model this and they drag these manipulatives over, these rods over, they will see, and you can ask the question in terms of how many times does a 1/2 go into 3, or how many halves will fit into 3, just like the cookies. How many groups of 4 cookies are in 20? You can ask the same question, only with fractions, and that will help keep the meaning of the operation intact for the students. And with this visual, they will see that 6 1/2 pizzas fit into 3. Now, dividing by a unit like this is a key towards understanding the invert and multiply procedure. So we need to generalize something here. Because obviously 3 times 2 equals 6. We know this. 3 divided by 1/2 also equals 6. And we can see that right there in front of us. And so we need to have this conversation with the students as to why does this work? Well, it works because the whole is divided into 2 pieces. Each of these wholes is divided into 2 pieces. So there are 2 pieces here, 2 pieces here, 2 pieces here. There are literally 3 groups of 2. 1, 2, 3. So by virtue of dividing the whole into halves, we have created groups of 2, which allow us to multiply by 2 to get 6. So we're getting a little bit of insight as to why this invert and multiply algorithm works. Why does multiplying by the reciprocal work? At least we have it with the unit fraction. And it would be worthwhile demonstrating this idea with several different questions so that kids can see that it works all the time. So we might have a question like, well, I don't know, there are, in this case, there are 2 pizzas, and they're making the portions extra small today, so it's 1/3 of a pizza for a portion. So how many portions can be made in this situation? If I've got 2 pizzas, well, let's take a look. So I've got my 2 pizzas. How many thirds can I get out of that? Well, there are my thirds. Now you can see, because they're thirds, we get 3 of them in one pizza, and that means we're going to get 3 of them in the other pizza, from the other pizza, and our answer again is going to be 6. We get 6 1/3 slices of pizza from each pizza. Get down there. So again, here's the generalization. If I'm dividing by a fraction in the form 1 over n, n is the number of pieces that is created. So if I want to know the number of pieces, I need to multiply by n. So we see that division by 1n creates the same product or same answer as multiplying by n. Okay, and this is an important idea to consider as we move forward into looking at the invert and multiply algorithm, which we'll tackle that in the next video.